Now we turn to recurrence and transience as far as random walks are concerned under stochastic processes. So recurrence and transience, the core idea here is this, that if we consider a stochastic process, e.g. a Markov chain, starting from a state I, a recurrent state is one that the process returns to with probability 1. So if there's a guarantee that a state will be returned to, you call that a recurrent state. Then you have a transient state, and it is one that the process may never return to. So once that state is left, you never go back there. So in short, recurrent means guaranteed return, while transient means possible escape. Okay, so the formal definition of all this now, if you let PII n be probability of returning to state I in n steps. So after taking n steps, you come back to I. So that's PII. So you can define Fi to be probability of ever returning to state I. Then state I is recurrent if Fi is 1, right? If there's a guarantee that you're going to come back to that state I after n steps. So Fi so you say it is recurrent because the probability of coming back there is 1. Then if state I rather is transient, if the probability of ever returning to that state is less than 1, there's no guarantee. So you say it is transient. So the key criterion here, which is very important, is that a state I is recurrent if the summation from n equals 1 to infinity of PIIn is equal to infinity. So if you have if you have an infinite, if the summation of all the probabilities is infinity, then you see that the state is recurrent, meaning that there's a guarantee that you are always going to come back there. Then it is transient if the summation of the whole probability is less than infinity, that is, it is defined. This is often the most practical way to classify these states. So this is criterion for classifying the states. So the intuition here is that recurrent means you keep coming back forever, while transient means you might leave and never come back to that particular state. So random walk examples now. So random walk example, we have a 1D simple random walk. At each step, you move +1 with probability 0.5. 1D simple random walk, right? Then move -1 with probability 0.5. So the result is that the walk is recurrent. In that case, the walk is recurrent. You can always there's guarantee that you come back there. Then for random, a two-dimensional random walk, it is also recurrent, but it is marginally recurrent. But for a 3D random walk, it is ever transient. So there's a non-zero probability of drifting away forever. So there's a guarantee in the 3D random walk that there'll be a forever drift from that point. So let's look at this example. Consider the transition matrix, P 0.5, 0.5, 0.2, 0.8. We study return probabilities P11N. So we evaluate whether the summation from n equals 1 to infinity of P11N is diverges or converges now. So, we have the probability that uh, you 1 for instance is 0.5, probability 2 is 0.8. But let's see what we can do with this Python code for return probability. So we have 0.55, 0.55. So by the time we compute and do all the summation right here, we end up getting 14.59. So, and since 14.59 is guarantee is not infinity, it's not blowing up. We have a finite value, that falls under the categorization of PII being less than infinity. That means it is defined. So in that case, now we say the state is transient. So here now there's a non-zero probability of drifting away forever. Okay, yeah. So here we have 14.5. So the interpretation is that if the sum grows without bound, then we say it is recurrent. But this our sum converges to 14.59. Without bound means it goes to infinity. So we would have had a recurrent situation. But if the sum converges, then we say it is transient. So in that case, now it means that you have a high chance of leaving a state and never coming back there. So the fact remains that any finite irreducible Markov chain has all states recurrent. Any finite irreducible Markov chain has all states recurrent. Then we have for a biased random walk now. So a biased random walk is the opposite of a simple symmetric random walk where the probability of going to any state is the same, zero point 0.5 each. So, but for a biased random walk, at each step, you can move right to probability P and move left to probability 1 minus P, where P is not equal to 1 minus P, right? Because if P is equal to 1 minus P, imagine so when P is equal to 1 minus P, that talks about a simple symmetric random walk. P is equal to 1 minus P. That means you have P plus P equals 1. That means 2P is equal to 1. So if you divide both sides by 2, so 2P over 2 is equal to 1 over 2. So it means that P is equal to half. So in this case now you have a simple symmetric random walk. But for biased, so for biased random walk, P is not equal to 1 minus P, like that. So that's a biased random walk in that sense. So we come back here and see what's going on. So the result is if P is zero point 0.5, you have a recurrent state. But if P is not equal to zero point 0.5, you have a transient state. So even a small bias introduces a drift. So we can do a Python simulation too, as usual. Um, Imagine we have random walk, the probability is zero point 0.6, just a bit over zero point 0.5, and we want to simulate this in 10,000 steps. So first time we have 0.809, and then if you do it again, we have 0.789. You do it again, we keep getting values above zero point 0.5 like that. So we have 0.807 that's the chance of it. So that's the chance of transience or so. Then we have expected number of visits now. So we also want to check the expected number of visits in a walk. So you define the summation from n equals 0 to infinity of PIIN. So it is when you get infinity here, it means it is recurrent. When you get something finite, it is transient. So then we can talk about types of recurrence. So we have possible positive recurrence. In this case, we have expected return time is finite. Then we have null recurrent. That this returns with probability of 1. So expected return time is infinite. Then examples, you have positive recurrence now. Positive recurrence, you have an example of that in finite Markov chains. Then you have a null recurrent in 1D random walk and transient recurrent in 3D random walk. So you then have simulation setup. So for a simulation setup like that, you have so yeah, for this setup now we define a function called walk one dimension in 10,000 steps. Starting position is 0, and then we go on with this whole other thing. Then we also have a 3D component of the walk here. So I run this now. So we define two definitions, one for a one-dimensional random walk, another one for a three-dimensional random walk. And then here we want to visualize the results of the one-dimensional random walk, which is the recurrent one. So this is the kind of thing you get. The origin is at 0, and then you have all the whole walk around it like that. But for a three-dimensional random walk, okay, of course, if you keep running it, it keeps changing, like we already know, uh, like that. So if I run it again, the whole thing changes. So it keeps changing as we keep running. So it keeps changing, changing about the origin like this. So 3D, same. So now, like we already know that every 1D random walk is recurrent, every 2D random walk is recurrent, marginally recurrent at least. But for a 3D random walk, it's transient. So there's almost impossibility of returning back to to where you're coming from. So imagine you have the walk, this whole blue thing is walk one, and it ends at this point where you have dots, and then the walk two is the orange one, and it ends around here. Then end uh then the origin is this red now. So the walk starts from here. For blue, it stops here. For orange, it starts and goes and stops here. Then for walk three, which is the green one now, so it starts from around here and it goes here. So you have it transient, but of course, as you keep running the code, it keeps changing too. And we have walk one final position. All of that information is giving a distance from origin 58.99. So you can compute all of that here. So if you run it again, you keep having different uh different things like that. So average final distance from origin for 3D works, you can also have the 59.9. So I think we should pay attention to that too. So we run this now. You have work one, final position 1648 minus 20. Work two, final position 2852. Final position minus 36 minus 34 minus 8. Distance from origin, you have all this. Then you have an average distance for 3D works. That's 53.97. So as you keep running, you keep getting different results like this. So now you can see the work here is not as wide as what we got before. This is 28.4 on the average. And then you have each one from work one, work two, work three, like this. So that's 3D work. So we have some key theorems. Theorem one, for instance, tells us that if a Markov chain is finite and it is irreducible, then all states are positive recurrent. Where we are going to talk about Markov chains in the future, so not to worry, we'll get to that point when we talk about Markov chains. But now we are still focused on random walks for the most part. So if a Markov chain is finitely reducible, then all states are positive recurrent. Then theorem two talks about random walk dimension. So one-dimensional random walk is recurrent, two-dimensional is recurrent. That means there's a guarantee that you come back to the state, to whatever state you live. But 3D plus is transient. That means there's every chance that when you leave a state, you don't ever come back there. In summary, we say that talking about return probability, the return probability to any state in recurrent for a recurrent random walk is one. For transient, it is less than one. Then for visits to a recurrent point, a recurrent state, you have infinite visits, but to a transient case, you have finite visits. Then for the summation of all the probability of being able to return, it's infinite for recurrent and finite for transient. So the key insight you draw from here is that recurrence means guaranteed return. So you can always return home. But transience is you're passing by. That means there's every high chance that any state you pass through, you don't ever come back there. That's it's more like you're escaping from that state permanently once you pass through. So it's more like you're in transit, you just pass through the place and you keep going. So basic understanding now for practice problems, define recurrence and transience in terms of return probability, Fi. Of course, Fi equals 1, that's recurrence. Fi less than 1 is transience, right? That's Fi is the probability that you return to whatever state. So in a recurrence, Fi equals 1. That means there's guarantee that you come back to the state. But for transience, the probability is less than 1. Show that if Fi equals 1, then the state I is recurrent. Of course, that goes without saying. Explain why a transient state must have Fi less than 1, because there's no guarantee that you come back to the state. So Fi has to be less than 1. Interpret the meaning of this now. So PII, summation of PII equals infinity. That means there's infinite possibility of going back to a particular state. So and that means recurrence for sure. Then we have computation and classification. So given 1, 0, 0.3, 0.7, classify each state as recurrent or transient. Okay, recurrent or transient. So we can use the code we used before for this kind of thing and see how it goes. Then for a two-state Markov chain like this, determine whether the chain is irreducible and classify states. We're still going to talk about Markov chain in some depth. So for now, we're just passing by. Then random walks now show that a 1D simple symmetric random walk is recurrent. Okay. It's recurrent, yeah, because P equals 0.5 talks about recurrence and P equals 0 minus 0, P not equal to 0.5 makes the walk transient. For a biased random walk with P equals 0.7, argue intuitively why return probability is less than 1. Of course, we already saw that once anything is not equal to 0.5, then it is transient. And that means probability of return is less than 1. Compare recurrence behavior in 1D and 3D random walks. Of course, recurrence is guaranteed in 1D. In 3D, no guarantees. Things are transient there. Then series and expected visits. Evaluate whether the series this suggests recurrence or transience. So as n approaches infinity, we have 1 over n. We didn't see cases of this. So you have 1 over n. Evaluate this now and relate. So I want to believe that this is about. So if once, okay, this n, now if you evaluate 1 over n, as n approaches infinity, you have 0. So that converges to a particular value. So I want to believe, based on, given that idea, it means that you have recur transience because it converges. But if it doesn't converge, then that's something. That's my hunch because we didn't do exactly this kind of thing. Show that if this is less than infinity, then the expected number of visits to I is finite, of course. Because the probability of return is not undefined, it's finite. So that's the deal. Then advanced concepts now. Distinguish between positive recurrence and null recurrence. We saw all of that. Give an example of a null recurrence process. Show that recurrence is a class property. Prove that a transient state is visited only finitely many times in expectation. Consider a Markov chain with one observing state. Classify all states as recurrent or transient. Yeah, when we get to Markov chains, we'll talk about that in some depth. Okay, so with this, we come to the end of this interesting video about recurrence and transience, where recurrence means guaranteed return and transience means possible escape, like no guarantee of returning to any state you have left already. Okay, let me know how helpful this is for you, and if there's something else you're going to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you have not subscribed, go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first or being the only one to see some videos as a member of the channel. You can request for PDF copies of my notes, with which I teach. We can hang out together online or physically if you're in the same geographical location at any point in time to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, anything at all that may be of interest to you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here till I come your way again. Keep doing maths right. Bye.